In this example, we are asked to look at the free vibration response of the 2-degree of freedom system that's shown there in the figure. We're given that it starts out from rest. It's given with displacement given for the particle on the left, where the particle on the right is in its undisturbed state. What makes this problem different than other ones we have done is if we look at the coupling between the two. That's alpha k, where alpha is small. And so that's what our focus is going to be, is what does the smallness of the coupling between those two masses have to do with the response? Okay, so let's begin here by writing down our usual steps here. We start out with T. Kinetic energy is 1/2 mx1 dot squared. x1 and x2 are absolutes, so T becomes this. Again, since they're absolutes, the potential is going to be equal to 1/2 kx1 squared. That's the spring on the left. The spring in the middle is 1/2 alpha k times the relative displacements between 2 and 1. So it's x2 minus x1 squared, plus the spring on the right is 1/2 k x2 squared. So our standard approach here for writing down our mass and stiffness matrices, the mass matrix is diagonal M. Our stiffness matrix is not. It is symmetrical, of course, using Lagrange. So this is 1 plus alpha times k minus alpha k and the 1, 2 and the 2, 1. And the 2, 2 is the same as the 1, 1. It's 1 plus alpha times k. From this, we will calculate our natural frequencies. Natural frequencies, as always, will set up the characteristic equation by taking the determinant of the matrix of minus omega squared m plus k, and we set that determinant equal to a 0. So the determinant here is going to be minus m omega squared plus 1 plus alpha k. The 1, 1 and the 2, 2 are the same, so that becomes a square, and then minus alpha k squared. So when I expand this out, I get m squared, omega to the 4th, minus 2m, 1 plus alpha k, omega squared, and then we have 1 plus alpha quantity squared minus alpha squared, all times k squared. So the characteristic equation, of course, is quadratic in omega squared. So we solve that quadratic equation for the square of our two natural frequencies, omega 1 and omega 2, and I get 2m quantity 1 plus alpha k plus or minus the square root of the 2m 1 plus alpha k, that quantity squared, minus 4 m squared 1 plus 2 alpha. And that, and the bottom, the denominator there is a 2m squared. Okay, so what do I get when I do that? It ends up being a fairly simple expression. No approximations here. This is 1 plus alpha plus or minus n alpha times k over m. So therefore, for omega 1, what I'm going to choose is the minus sign. So omega 1 then is the square root of k over m. The negative sign, the alphas cancel out. Omega 2, they don't. And omega 2 ends up being the square root of 1 plus 2 alpha times the square root of k over m. So these are the exact natural frequencies. This is valid for any value of alpha. We still haven't said yet that alpha is small. Our modal vectors. We have two equations that we can use. Looks like I chose to use the first equation. And the first equation from our eigenvalue problem is going to give me the ratio of x2 to x1 for the jth mode of being minus m omega j squared plus 1 plus alpha k divided by alpha k. So if I simplify this just a bit, I end up with 1 plus alpha minus m over k omega j squared times 1 over alpha. So I will let the first position be a 1, just like I've done, or we have done in all of our examples. So that's chosen to be 1. As a result, then, our two modal vectors, x1 and x2, are 1 minus 1. I'm sorry, that should be a 1, 1. And the second modal vector, x2, is a 1 minus 1. I will mass normalize. The mass normalization, again, is a not necessary, but it's a convenient step in order to find the free response. So the mass normalization, that's done, of course, as we've done before, by taking the modal vectors that we've already found and dividing by the square root of that corresponding modal vector transposed in post-multiplied by the same modal vector with that square root like that. So from this operation, what I get is that x1, the mass normalized modal vector, is a 1, 1 scaled by 1 over square root of 2m. And the second mass normalized modal vector is 1 minus 1 with the same scale factor in front, 1 over square root of 2m. Our response. We'll use the usual process here. The response is that we start out with initial conditions of giving a displacement to mass 1, but not to mass 2, and we started out from rest. So the initial x dots are a 0. So using our basic operation here, C1, which is therefore x1 transpose the mass normalized one times m times x1 ends up being a square root of m over 2 all times a, C2. Same thing except the 1 is replaced by a 2. And it gives me the same thing, square root of m over 2 times a, with our initial velocities equal to a 0. That is 1 over omega j x J transpose, mass normalized, times M, post multiplied by, it looks like I got carried away here. All of these here should be reflecting on the right-hand side my initial conditions. So let's make the correction here. This should be the initial displacement on X. Initial displacement X. This is the initial velocity. And since the velocities are both a zero, so do our response coefficients. So again, everything that we have up to this point is exact. No approximations have been made to tell us that this coupling is soft between the two. But here's where we begin that. If we consider small alpha, light coupling, we have a term here, 1 plus 2 alpha, which is appearing in our second natural frequency. So what I'm going to do is a Taylor series expansion. About alpha equal to a 0. So what I do is I take the function and evaluate it at alpha equal to a 0. I take a derivative of that function with respect to it. Alpha, I get 2 divided by 2, 1 plus 2 alpha, now to the 3 halves, evaluate it at alpha equal to 0 times alpha, and then I get more terms. But what I'm going to do is I'm going to truncate that Taylor series expansion after the linear term. The first term that I left off is an alpha squared. So this ends up being 1. That's the first term. Next one ends up being an alpha dot dot dot. And we'll say that for small alpha, we'll neglect. What does that mean? Well, the reason for doing this is that we were looking at omega 2. Omega 2 was 1 plus 2 alpha raised to the 1/2 times the square root of k over m. So it looks like then omega 2 is approximately equal to 1 plus alpha times the square root of k over m, which is equal to 1 plus alpha times omega 1. So omega 2 differs from omega 1 by small proportionality. The two frequencies are close together. And they're so close that whenever later on I'm going to use these two results here, if I need the average value of those two, omega 1 plus omega 2 over 2, that's omega 1 plus 1 plus alpha omega 1 over 2. This is equal to omega 1 plus alpha omega 1 over 2, which is roughly equal to omega 1. Where the difference of the two becomes important, omega 2 minus omega 1 over 2, that's 1 plus alpha omega 1 minus omega 1 divided by 2. And this is exactly equal to alpha omega 1 over 2. So the difference becomes an important a number here. That difference is small. It's proportional to that value there of alpha. So what I will do is I will write down the response for x1 and x2. So using our free response coefficients that we just found for C1, C2, this becomes C1 cosine omega 1t plus C2 cosine omega 2t times 1 over square root of 2m. That factor comes from the fact we mass normalized our modes. So we put in C1 and C2, we end up with 1/2 times A times cosine omega 1t plus cosine omega 2t. So that's just the way that things work out. I'm going to use a trig relationship here. This trig relationship that I'm going to write down is equal to, with the half there in front, that ends up being cosine omega 1 plus omega 2 over 2t times cosine of the difference of omega 2 and omega 1 divided by 2. So this is really why above I wanted to find out what the value was for omega 1 plus omega 2 over 2, and the difference right here. So what this says is that for that trig identity, what we end up with is A times cosine alpha omega 1 over 2t and cosine of omega 1t. Why is this important? Well, this, we see, is low frequency. As alpha becomes small, as the coupling becomes small, alpha is small, that means that this multiplier in front is low frequency. And this is an amplitude modulation. This is the low frequency amplitude envelope, if you will, where this is at frequency omega 1. So the first natural frequency dictates the second term, but the one that is in front is dictated by the difference between those two. If I do the same thing for x2 at t, using my response coefficients found above, that's C1 cosine omega 1t plus C2 cosine omega 2t. That's not a plus, but that's a minus, just because of the way the mode shapes turned out. So that's a minus sign. If I can get that erased here. It's a minus sign. And I get the scale factor there in front, 1 over square root of 2m. And putting in C1 and C2, this becomes 1/2 A times the quantity of cosine omega 1t minus cosine omega 2t. Again, that's just using the results for response coefficients C1 and C2. Using a trig identity, this becomes a minus A times sine of alpha omega 1 over 2t sine omega 1t. So again, what I've done is I took the same trig identity idea from before. It gave me a slightly different result. It becomes in terms of sines rather than cosines. But you get the same kind of thing. This is a low frequency amplitude envelope. That envelope is going in front of or multiplying a contribution which is at the frequency, same one, omega 1. So what does this mean? Let's say it in words what the math is saying in terms of these equations. So for our discussion, there's a couple points to be made. The first point is that both x1 and x2 have a low frequency amplitude modulation. And we got this by looking at alpha as being small. The frequency of the amplitude modulation is equal to alpha times omega 1 divided by 2. In other words, as alpha becomes smaller, the period of the amplitude modulation goes up. And note also that the x to a t amplitude modulation, which is sine alpha omega 1 over 2t, is 90 degrees out of phase with the x1 of t amplitude modulation, which was cosine. So what does that mean in terms of how the response looks? Well, let's make a sketch of x1 and x2. I'm going to draw x1 axes right here. And right underneath it, I'm going to draw x2. And what I'm going to show here in blue is going to be the amplitude modulation. So this is x1, this is x2. The amplitude modulation, recall went as cosine. The cosine looks like this. And so the frequency in psi, which goes as omega 1, is a lot higher in frequency. So it looks like this. So the period that goes along with this signal here is 2 pi over omega 1. The period that goes along with this one here, the actual period from here to here, that ends up being pi over alpha omega 1 over 2. Now the x2, again, it differs because the amplitude modulation that goes is sine. So let me do my best job here of making that sketch. So the sine is 180 degrees out of phase from the cosine. You'll probably do a lot better than I do on this sketch. But definitely show this as being a sine wave modulation over a signal of sine that looks like this. And again, because The modulation is cosine in one and sine in the other. The blue envelopes are 90 degrees out of phase. Anyway, the point of this example is that when you have systems with frequencies that are close together, if they are modally coupled, then you should fully expect this kind of response, because it's in any system where you add together two harmonics like cosine or two harmonics like sine, where the frequencies are very closely spaced. It all comes back to really trig. Right here, this trig relationship is what tells us that. It comes out anytime your frequencies are close together, the sum becomes something like a sum and a difference divided by two of those. One, if that difference is small, that gives you a low frequency amplitude modulation.